Welcome back. This is Functional Analysis FAV 004 by Professor Dr. A.G. Srinivasan. Before the examples in metric space, we first give some important spaces which we'll be investigating throughout this course. R, set of all real numbers. Q, set of all rational numbers. C, set of all complex numbers. R2, the Cartesian product of R with itself, called Euclidean space. For a fixed n, a natural number, Rn is n Cartesian product of R. This is also called as Euclidean space. If you replace R with C, the complex numbers, set of all complex numbers, Cn is called a unitary space or complex Euclidean space. In the context of complex Euclidean space, this is called a real Euclidean space. We also introduce LP space in the subsequent lectures, L infinity space. These two spaces are going to play a very important role in functional analysis paper. We introduce C of AB, a set of all functions from A to B to R or real numbers, A to B a closed interval of R, a subset of R, where F is single valued function. Also, it is a continuous function from the calculus sense. This is CAB, a set of all single valued continuous functions from the closed interval AB to R. B of A, a set of all functions from A to R, where A is a subset of R such that F is bounded. In video 6, we will tell you what is a bounded function, bounded sets, etc. Let's continue with examples of metric space. We begin with x is equal to R. First example, define d of xy is modulus of x minus y. Now, showing the properties of the metric space is very obvious. First one is non-negative, that can be checked with this modulus, and this is equal to 0 if and only if this is equal to 0, therefore x is equal to y, and d of xy is same as d of yx because of modulus again. So using mathematics and properties of modulus, it is easy to verify xd is a metric. And to show the triangle inequality d of xy, modulus x minus y is less than or equal to x minus z plus z minus y, and use modulus property, it is easy to show that d of xy is a metric space, and this d is called a standard metric for R. Example 2, x is equal to R2. R2 is the Cartesian product of R with itself, called a Euclidean space, okay, where x equal to a component a1, b1, y is equal to a2, b2, where a1 is on R, b1 is on R, a2 is on R, b2 is on R. We define d of xy is equal to square root of a1 minus a2 to the whole square plus b1 minus b2 to the whole square. Now, proving this metric is very immediate because view this as a point. a1, b1 is one point, a2, b2 is another point. So distance between 2 points can be viewed. You can draw and explain using the distance functions. Usual distance in real number system, you can show it's easily a metric, so that we leave it as an exercise. Example 3, generalizing. Take x is equal to Rn in a Euclidean space. X is equal to a1, a2, etc. an. Y is equal to b1, b2, etc. bn, where each ai and bi belongs to R. a1 belongs to R, a2 belongs to R, an belongs to R, b1 belongs to R, b2 belongs to R, bn belongs to R. Define the metric d of xy is square root of a1 minus b1 the whole square, the component wise difference and square it, plus a2 minus b2 the whole square, etc. an minus bn the whole square. It is almost same as that of 2 because we have done for a distance using geometry and using a point in a graph xy axis. This can be generalized in a similar way. So therefore, the proof is left as a practice exercise. So proof follows immediately as an extension of d of xy, the Euclidean metric we discussed. Example 4, instead of Rn, we have taken Cn, where x is equal to a1, a2, etc. an, y is equal to b1, b2, etc. bn. Now, in the previous example, as and bi's belongs to R. Now, a and bi belong to C. So, define d of xy is equal to modulus. Okay, complex numbers, modulus is been taken. If z equal to a plus ib is a complex number, modulus of z is square root of a square plus b square. When you square it, you get a square plus b square. So, we are taking the modulus of the individual components of differences a1 minus b1 the whole square modulus and square it. Using the similar proof of example 3, you can show that it is also a metric space. If n equal to 1, this is same as this is same as this e1 same as this, if of course r is equal to c. If you have taken instead of complex numbers pure real numbers with the imaginary part is 0, then the usual metrics, the metrics given as a Euclidean metric, the unitary metrics become the standard metrics. I am Dr. A.G. Srinivasan. We will see you soon in the next video, FAV 005. Thank you.